so you've had a chance to do some setup ahead of time. There are two things that you need to do. One of them is get my repository, which is the Think Complexity 2 repository. Anybody not have that? I've got it on a thumb drive here if you need it. There's a folder on there called Think Complexity 2, so just make a copy of that. That'll be all the files you need. And then the software you'll need is either Python 2 or 3. Everything we're going to do works with both of them. And then a setup that's got the usual Python science stack, the SciPy, NumPy, Jupyter, all that stuff. If you've got a pretty standard Jupyter installation, you probably already have everything you need. The one thing you might not have is FFmpeg, which will make the animations work. FFmpeg has turned out to be kind of a pain. So if it works for you, great. If it doesn't, you won't be able to see the animations on your laptop, but to be honest, it'll be OK anyway. So if it works for you, good. If it doesn't, don't worry about it. And we'll get started in just a couple minutes. Anybody, any questions about setup stuff? OK. No. OK, good morning. If you're in the right place, you should be here for complexity science. If you're not here for complexity science, this would be a good time to kind of sneak out of the room quietly, and we'll all pretend not to notice. I'm Alan Downey. I teach at Olin College, which is a new engineering school. We're just outside of Boston. Our mission is to fix engineering education. And one of the ways that I'm working on that is a series of books that use computation to study lots of different topics. And the one we're going to do today is complexity science. Complexity science is sort of a weird collection of topics. And one of the things I want to do with the workshop today is engage you in thinking about, what is this? Is this useful? I was talking to someone before we got started about, well, what are the real world applications of what we're doing today? And the answer is, I don't really know. I think it's an interesting set of topics. I think it does have applications. But that's one of the questions we'll wrestle with over the course of the tutorial. So one definition is that complexity science is about the modeling and simulation of complex systems, not the most useful definition. What a complex system is a system that's made up of components. They interact with each other. And very often, the way we're going to represent that system is by a network that has nodes for each of the components and edges that represent the interactions, or links that represent the interactions. Another way of thinking about what complexity science is that it's different from previous kinds of science. So this is a range from very simple things on the left, often the study of or the science of a single atom, or a single particle moving through space, or two particles that interact with each other. So on the left, we have a lot of physics that is about very small systems. On the right, we have some physics that is about very large systems, like very large numbers of atoms. When they interact, you get things like statistical mechanics, where you can describe how the group will behave as an aggregate. What's interesting is the middle. Complexity science is about this middle part where you have too many components to do simple physics, but not enough components to do statistical aggregation. It still matters what the individual components are doing. So complexity very often is in the middle of these ranges. Historically, complexity is the most recent area of science that the science of the very few really started in the 1600s. We have things like Newtonian mechanics that do a great job of explaining celestial mechanics, for example, how planets orbit suns, where you basically have two things that behave like a point mass, and they interact in relatively simple ways. At the other end, we have statistical mechanics and thermodynamics, mostly from the 1800s. The middle, complexity science, is relatively recent. It's mostly the late 20th century. And it's the late 20th century for a good reason, because that's when we got computers. So complexity science and computational power kind of go hand in hand. One problem with physics education or science education more generally is that it tends to go in historical order. That probably everything that you studied in high school had been discovered in the 1700s. You probably didn't learn anything in high school that was less than 200 years old. And if you took more physics in college, you maybe got into the 1800s. But chances are, unless you took quantum mechanics, you probably didn't learn anything from after 1900. And that's a shame, because you also probably didn't get into complexity science. So here's my claim. I think complexity science will turn out to be useful. It also turns out to be, I think, just interesting to think about. There are a bunch of questions that are going to come up that get right to the philosophy of science. Over the course of the tutorial, I'm going to take some detours in those directions. There's also some elegant examples here of very simple models that do surprisingly interesting things. And the last part is, I think it's just fun. There's a lot of this that is just fun to play around with. So the three things I'll talk about today, we'll start with agent-based models. We will talk about cellular automata, which is hard to say, and random graphs. So three big chunks today. And as I said, a couple of interludes where we'll get into some of the philosophy. Hopefully, I will give you a sense of what this is like. We will ask this question of what it's good for and poke at some of these questions that it raises. And then at the end, I'll have some suggestions for additional reading and other things that you might want to do. So the first example we'll do is an agent-based model. If you're interested, one of the first resources I'll point you to, this is an article in The Economist from a couple of years ago talking about the growth of agent-based modeling and its use in economics, other social sciences, and in the natural sciences. So the first model I'm going to run through is from 1970. So it's one of the earliest examples of agent-based models. It was proposed by an economist named Thomas Schelling, and it's a model of segregation in housing, like segregation in a city. So here's what the model looks like. We've got a grid world where everybody lives on a block in a two-dimensional grid. And there are two kinds of people. There are red people and blue people. So everyone has 8 neighbors on this grid. And each agent looks around them at the other neighbors to see how many neighbors are like me. And if there aren't enough, if I'm feeling outnumbered in my neighborhood, then I'm unhappy in the terms of the model. I'm unhappy. And so I choose a random location and I move. And that's it. That's Schelling's model. So let's get into the repository, and we'll get a chance to run this example. We'll do a little bit of setup. How many people have not used Jupyter before? Oh, OK, pretty good crowd for Jupyter. Let me show you what this is going to look like on my setup. It might be a little bit different on yours, and then we'll get into the first notebook. So if you've cloned my repository, you should be able to cd into Think Complexity 2. And then if you want, you can also cd into the code directory. That part doesn't matter. And then when you launch Jupyter on the command line, if you run Jupyter Notebook, so there are two parts of Jupyter. We're going to run the server in this window. So when you launch the server, two things happen. One, you get a message from the server that says, I'm running now. And then the other, Jupyter will grab your browser and either launch a browser or open a window. And it will connect you through the browser to the server. And in this case, it's showing me the list of files that's in that repository. And chapter 9.ipynb is the one you want. So that'll open the notebook. The notebook is organized in cells. The cells can be text or code. And the magic command that you need to know in order to run Jupyter is shift return. So if you start out in any cell and hit shift return, it'll execute it. When you run a text cell, it just formats the text. The key thing here when I run this code cell is it'll import everything I need. And if it runs and doesn't complain, then that means you've got everything that you need for the workshop. If you get any error messages there, it probably means you need to install something. So if you see something that you don't know what it is, let me know and I can help you debug. If that's working, then go ahead and start reading through the notebook and run the code. You don't need to read all of this code. I'm going to come back and explain some of that. But starting from here, you should have a good understanding of what's going on. I'm instantiating a model, I'm creating a viewer, and I'm drawing the setup. So read through that. Just read through the first section, which is called Schelling's model, and then we will regroup. And I'll come around. If you have any questions, I can help you get set up. All right, let me get you back for just a second. I want to talk through a little bit of the code so you have a sense of how it works, and then we'll look at some of the results. So the first part, I need a grid that represents this world, where, as I said, there are two kinds of people, red and blue, and I need a certain number of empty cells so that when an agent is unhappy, they're going to choose one of the random empty cells, and that's where they're going to move to. So I'll just do a swap. I'll need to be able to swap an agent into an empty cell. So I'm going to use a bunch of NumPy. Just out of curiosity, how many people have used NumPy before? OK, good. So probably some things you've seen before. If there are some new things, that's even better. So first part, I'm going to set up my set of choices is 0, 1, or 2 to represent empty, red, or blue. And then the probabilities are 10% empty, and then the other 90% is split 50-50 between red and blue. And then I'm using numpy.random.choice in order to generate the initial grid. So this is what the world looks like when we start at random. And there's what that looks like. And I've got this function called segregation that computes how segregated the world is by taking each agent and counting how many of its neighbors are the same color, and then averaging that over all the agents. So if I completely randomly generate the world, I would expect it to be approximately 50-50. And sure enough, in this example, it comes in at about 46%. So that's about what I expected. So that's random world. And now I want to figure out who's unhappy and start swapping agents around. This is the dynamic part of the model. So the first part, I'm going to make 3 logical arrays. In each case, I'm going to take my grid, and I'm going to select all the elements that are 0. So empty is going to be Boolean. It'll be true and false. It'll be true where a cell is empty and false elsewhere. And similarly, red is going to tell me where all the red agents are, and blue tells me where all the blue agents are. Now I need to count up for each agent how many of the neighbors are red and how many of the neighbors are blue. And to do this, I'm going to use the correlate2d function that comes from SciPy. And I'm curious to know how many people have used correlate2d before. OK, many fewer. That's good. This is a nice tool to know about. This is useful for doing a lot of operations like this, where you need to go through an array and perform an operation on each element of the array that has this pattern to it. And the pattern is that I'm going to take a small array that's called a kernel that's like a rubber stamp. So I'm going to take this stamp, and I'm going to apply it to every agent in the grid, one at a time. And what apply means is that I'm going to multiply the kernel times the input array, and then add up the product. And that'll give me what's in that diagram, the red dot. So in this example, I've got the dark blue dot is the agent that I'm currently looking at. The light blue dots are the 8 neighbors, and I'm going to add them up. The reason I'm adding them up is that my kernel is 1, 1, 1, 1 for each of the neighbors, and 0 in the middle, which means that I'm not counting myself. I'm only counting up the 8 neighbors. So if I do a correlate2d, and I apply this kernel to the red array, then it will count the number of red neighbors for each agent. If I apply it to the blue array, I'll get the number of blue neighbors for each agent. And then I'm just going to add them together. That'll tell me the total number of neighbors for each agent. Good so far? Any questions about correlate2d? This is going to come up several times, and we'll use it in a couple of different ways. Now, to figure out who's not happy, I'm going to compute for each agent the fraction of neighbors who are red and the fraction of neighbors who are blue. That part's easy. That's just division. So I'm taking an array, and I'm just dividing through by a constant. Okay. So instead of counts, now I've got fractions. But now I want to know, for each agent, how many agents are like myself. And for that, it's kind of like an if statement. I want to say, if I'm red, then I care about the fraction who are red. And if I'm blue, then I care about the fraction who are blue. So what I want is the NumPy version of an if statement. And that's what the where function is. And now I'm curious, how many people have used the where function from NumPy? Excellent. So this is like an element-wise if statement that says, where the agent is red, I want you to select the corresponding element from frac red. And else, must be blue, select the fraction of blue. Okay? So after that where statement, now I have an array that shows me for every element, for every agent, what fraction of the neighbors are like that agent. I need to do a little bit of cleanup because there are some empty cells. And so for those, I'm going to put an np.nan, which is not a number, which is a standard way to represent something invalid or missing data or unknown. So not applicable is what I'm going to put there. And then finally, I can check to see whether an agent is unhappy by checking to see whether the fraction of sameness falls below some threshold. So these agents, they don't mind too much if they have a few neighbors who are red and a few neighbors of blue, but there's some threshold that I'm calling P that is the threshold of unhappiness. If let's say only 10% of my neighbors are like me, then I'm going to pack up and move. Okay. Now, I had to do a little bit of installing to see if I could get animations to work for me. Hopefully, they're working for you. I'm going to do a kernel restart. Actually, just a restart. Kernel restart and reload. See if I have better luck this time. So there's the initial condition again. The level of segregation is about 50-50. That's what we expected. And now, oh, wouldn't that have been nice? All right, looks like I'm not going to be able to run the animations, but we can see this figure that shows what the world looks like after 2 steps and after 10 steps. And one of the things that's kind of surprising is after only 2 time steps, so during each time step, each agent looks around at its neighbors, decides whether to move, and if below some threshold they move. After just 2 time steps, that's that middle figure, you're already seeing clusters forming that are either all red or all blue. After 10 time steps, it's a pretty highly segregated neighborhood. And if you run this plot, it'll show you, for a couple of different values of P, what happens to the level of segregation over time. So one way to read this, so the bottom line there, the light blue line, says that P is 0.2. And that means that people are actually pretty happy living in a mixed neighborhood. They're totally OK. But if it gets below 0.2, that's a pretty low threshold. And that's not too bad. In terms of the outcome, you get a little bit of segregation. When P equals 0.2, it looks like the level of segregation gets up to maybe 0.55. Maybe that's not so bad, depending on your criteria. But as soon as you get to 0.3, now 0.3 is kind of moderate. What that says is, look, out of my 8 neighbors, if 3 of them are like me, I'd be perfectly happy. That's 0.375. So I'd be happy with 3 neighbors who are like me. But the actual level of segregation that I get is in the high 70s. So even though I would be content with 30% of my neighbors being like me, what I actually get is 70% of my neighbors who are like me. And you can see that in the model that happens very quickly. And it's more severe as P increases, the overall level of segregation increases as well. Make sense? Any questions about what we're seeing? Yeah. Mm-hmm.
Is that just because you randomize all of the unhappy neighbors and that's where it lands? Or?
Good question. Let me paraphrase it if I can. What you said is it doesn't seem to make logical sense that this is happening, that gap is as big as it is between P, which is relatively low, and the actual amount of segregation that we get. And I think you were asking, is that happening because all of the neighbors are kind of acting at the same time? Yeah,
Or what is your thinking as to why that happens?
Right. So this is an example of emergence. This is an example where, from understanding how the agents behave, you might not expect the system as a whole to behave the way it does. This is a relatively simple example. We're going to see more. But this is exactly the kind of thing that you get from complex systems, which is that the system as a whole exhibits behavior that you wouldn't expect based on a simple description of the agents and how they interact. Let's see, just one other small bit about the computation. So when I compute the level of segregation, I'm using nan mean, which is a nice feature in NumPy. It'll compute the mean of an array while ignoring any nan elements. So remember that I put in nans to represent the empty cells, so I don't want to count them when I compute segregation. There's the figure we were just looking at. And again, this is the striking part of this. The threshold point 3, I think, is the interesting point because that's where that gap is the biggest between what the agents prefer and what they actually get. It's not so surprising. If the agents are radically xenophobic and you get segregation, that doesn't seem particularly surprising. But point 3 doesn't seem radically xenophobic. All right. You might at this point be thinking, well, all right, that's an interesting mathematical toy, but it's a ridiculously simple model of the world. And in fact, when Schelling started doing this work, that was pretty much the reaction he got, which is that this is just stupid. People are complicated, and you are boiling them down to these agents that do a simple mathematical calculation, and then they make decisions. What could a model like this possibly say about the world? So I want to speculate on this a little bit by contrasting the kind of work that we sometimes do in complexity science with what I'm going to call classical science, classical physical modeling. And I want to contrast two kinds of why questions. So one of them is why planetary orbits are elliptical and why why cities are segregated. So we have a really good answer to the first one. Classical physical modeling is based on physical laws, usually continuous mathematics, and things that look like proofs and mathematical derivations. So if you give me the law of universal gravitation and you give me Newton's laws of motion, I can write a differential equation, I can solve that differential equation, and I can show you that the solutions are ellipses. And that feels like a really satisfying answer to a why question. Why are planetary orbits ellipses? Because physical laws, mathematical derivation, QED. It looks like a mathematical proof. In fact, it looks like we proved something about the world. And if you take a physics class, you would often leave thinking that you proved something about the world. But you didn't. You proved something about a model, because the equations that you wrote are only an approximate description of what's actually going on in the world. So thinking about that elliptical model, thinking about a planet orbiting a sun, what are all the things that we ignored in that model? What did we leave out? All the other planets and their moons and dust and all the other junk floating around in the solar system. What else? Sorry? We left out general relativity. We applied Newtonian laws of motion and didn't take into account relativistic effects. Turns out that that actually matters for relatively fast-moving planets. What else? I mean, those are a couple of the big ones. So really, the answer is, if someone asks, why are planetary orbits ellipses, the real answer is, well, they're not. If you want to know why they're approximately elliptical, well, it's because I have a model of the world, and the model is similar to the world. And so I think that the behavior of the model will be similar to the behavior of the world. But really, I'm making an argument by analogy here. I'm saying that because these two things are similar in one way, I expect them to be similar in another way. And it turns out the argument by analogy is pretty good as a heuristic, and it's gotten us this far. So I don't want to bash the argument by analogy too hard. However, the argument by analogy is, from a logical point of view, totally false. There's no reason to think that just because your model is right in one way, that it'll be right in other ways. Turns out to be often enough that we do pretty well in practice. The airplanes still fly, but we're out on a logical limb when we make this argument. Anyway, that's the argument from standard physical modeling. It's an argument by analogy. So what about Schelling's model? It seems like a strange kind of model because that first step where I say the model is like the world doesn't seem to hold up. In fact, Schelling is almost going to the opposite extreme and saying, look, this is the simplest possible model that I could make for this system. And if you're thinking like classical physics, then you're thinking, OK, that is such an unrealistic model, it can't possibly do any useful work. So that's my question, which is, does this model do any useful work? Let me pose that question in sort of a funny way, because this is an actual conversation that I had in 1989. When I mentioned that I was from Boston, I got a response that was pretty similar to this. It said, oh, you're from Boston. Boston is a very segregated city, so Bostonians must be kind of racist. So here's my question. Does this model, does Schelling's model, give us anything to say in response to this question?
Yes.
I hear a yes. Tell me what it says.
So my thinking is if everybody was really randomly segregated, you'd expect about 50% of the people, you'd expect 50% of the people to be like, you'd expect everybody to have 50% of the neighbors that they like or whatever.
Mm-hmm.
Like them. And so if you say, okay, anybody that's not happy, we're going to pull them out and randomly re-roll, you have to move the average up, and that's where your 0.7 or whatever becomes halfway between 0.3 and 100%.
Mm-hmm.
So I don't know that I've explained that very well, but I feel like in my head it helped me get it.
OK, good start. Anybody else? What would you say?
Well, it seems from this model that there's kind of a competitive dynamic going on, whereas
Mhm.
people become happier because they're around more people that are like them. That's correlated with those regions being too dense for the other group. So there's
Mm-hmm.
kind of a counteracting force.
Yes, OK. So there's some competition here between people who might be happy in their neighborhoods and people who are not. And the ones who are moving are creating segregated neighborhoods and effectively pushing others out. OK, interesting. Yeah.
How do you quantify kind of racist? And going back to this example, saying I want 3 of my 8 neighbors to be similar to me, most people wouldn't say that's racist, but maybe a way to flip this is to say, well, if 7 of my neighbors are the same, that's too much the same. I
Mm-hmm.
want to move it in. And maybe that would get us back toward closer to in between that 0.3 and 0.7 or something like that.
Right, OK. So you said 2 interesting things that I want to capture. One of them is, how do we quantify kind of racist? And you said, so maybe the threshold of 0.3, I don't know whether to call that racism or not. The other thing you suggested is looking at agents who might have a preference for mixed neighborhoods. In other words, they're unhappy if none of their neighbors are the same, but they would also be unhappy if all of their neighbors are the same. There are actually some people who have looked at versions of this model that do exactly that. Those are interesting ones, too. I don't want to spoil it, but I will say there are some versions of this model where even when people prefer mixed neighborhoods, you get lots of segregation anyway. But let me leave that aside for just a second. I have one other answer over here, and then I'll.
So this says that I observe segregation, therefore the individuals are racist. But looking at the Schelling's model, you can observe high amounts of segregation even with below p-values. And so even if the model is extremely simple, it's showing an example where observing the output doesn't prove your assumptions about the inputs.
Good. OK, let me see if I can repeat that. So you said the argument that my hypothetical date is making is that I see a segregated city and I infer that the people in that city are racist. And what you're saying is that, well, this model actually shows a counterexample to that. This shows at least one possibility where even if the people are, and again, maybe I'm not sure how to characterize them. I'm going to call them mildly xenophobic. If there's a possibility that if you just have people who have a little bit of xenophobia, you can get a highly segregated city anyway. Yeah, good. Yes, one more. Yep. Yes. Correct. That, yep. That is true, although the version that we've seen so far doesn't quite show that. So let me just clarify. When p is 50-50, when p is 0.5, that doesn't mean that the agents want to live in a 50-50 neighborhood. It means that they would only be happy with 50% or more who are like themselves. So that's actually a fairly high level of, let's call it xenophobia. Good, OK. So this is possibly Schelling's response is it is possible to get high segregation even if the agents are only a little bit xenophobic, and therefore you cannot draw the inference in the other direction. Just because you see segregation doesn't necessarily mean that there's racism. I will also point out it doesn't rule out racism as an explanation either. It just means that it's not logically required to produce segregation. OK. Yeah.
How does the model behave if red and blue have different p-values?
Excellent question. How does the model behave if the red and blue are not necessarily 50-50? That is the next exercise that we're going to do. So a couple of things that you can play around with on this model. The simplest one is exactly that. So often when we're talking about segregation, we're talking about a majority and a minority population. It might be interesting to take a look at that and see again what this relationship looks like between the threshold and the outcome, the measured level of segregation. So if you want to jump back into the Chapter 9 notebook, you can play around with that just by changing the probabilities. The other thing that you might want to try out is different agents who have different levels of p. It'll take a little bit more coding to do that. And then there are two others. I have some suggestions here. Depending on how quickly you're able to do this coding, you could do it now, or you might want to come back and play around with this later. You could try it out with 3 kinds of people and see what happens. It's not too hard to extend the model for that. And then the other one is the one that we were just talking about, which is what happens if people have 2 thresholds. They are happy in the middle and unhappy at the extremes. So you could try that one out. I'll come around while you're working on that, help you out with any questions. Okay, I tried out a couple of experiments up here. I'll show you. I didn't find anything super interesting, but I did one where I adjusted the world so that it's 10% empty houses, 10% red, and 80% blue. And what you get from this world is kind of a whole lot of segregation no matter what, because you got 80% blue. It's pretty hard to avoid having a bunch of blue neighbors. The other thing I tried out is a different value of p for different agents. And one way to do that is I replaced the old line here. Used to be just self.p equals 0.3. And instead, I generated a random array. Oh, actually, no, I need to change that. So that's not right. What this is doing is just picking one random value each time. So that's not doing anything useful. But if I change this to generate a random array, I need to specify the sizes n and m. And then that will allow me to, here, where I compare it, this line. So frac same, again, is the array that says for each agent, how many of my neighbors are like me. If I replace p with an array, then it'll be like having a different value of p for each agent. And so I'll do an element-wise comparison to see who's unhappy. So I haven't quite finished off that part, but I will leave that as an exercise. One other version of this model that I want to show you, we won't code this one up, but I'll show you a solution. So this is based on a book that's called The Big Sort. Has anybody read The Big Sort? Ah, OK. This is Bill Bishop made the observation that in the US, we certainly have racial segregation, but we also have political segregation, which is the tendency of people to live near neighbors who have similar political views. And his conjecture is that the mechanism is not so much that if I find myself surrounded by people who think differently from me, that I get unhappy and move. But he suggested that people move for random reasons. You get a new job or whatever. But when you move, let's say you're going to a new city, and you look at maybe two neighborhoods. And you notice that in one neighborhood, there are a lot of signs for one presidential candidate. And in the other neighborhood, you see a different presidential candidate. And maybe you're just more comfortable in one than the other. So there's a question, can we model that, where instead of people become unhappy and then move at random, instead people move at random and choose a neighborhood. Maybe they look at 2 or 3 neighborhoods and they pick the one that's similar to them. So it's pretty much the same setup as the Schelling model, still a 2-dimensional grid with reds and blues and so on. Any guesses about what this is likely to do? I hear the suggestion that this one might segregate just about as well. And sorry, what was the other? Looking very similar, yep. So if you go to, so this is one of the exercises in the book. And if you want to see a solution to it, we can go into the Chapter 9 solution notebook. Chapter 9 solution.ipynb. I'm going to skip over Sugarscape. Sugarscape is the other model that's described in Chapter 9. We won't talk about it today, but you might find it interesting to look at later on. And then the first exercise in the exercise section is the big sort. If you're a fan of object-oriented programming, you'll see that I've got a class that's called Big Sort that inherits from Schelling. So I have all the same functions that were in the Schelling class. Now I just have to override init, which is almost the same. The variable here that's called numComps is the number of houses that you look at before you decide which house to get to, which house to buy. And then my step function is kind of similar to what we saw before. It's moderately complicated to model. So each agent is going to look around, look at some number of neighbors, some number of neighborhoods, and choose the one that has people the most like themselves. And I forgot to execute that cell, which is why it was undefined. And here's what the output looks like. So I'll give you a second to run that. I'll come around and see if there are any problems, and then we'll take a look at it. I got one useful tip that I will pass on. In my original version of this, I had HTML5 here. It turns out that JS HTML at least worked for me. So if your animations are not working, you could try that out and see if it helps. I will show you. In the very first cell, there's an HTML5. This is what the big sort algorithm looks like. All right. And the results look like this. So the light blue line there is the number of comps being 2. So this says that if I think 10% of people move during each time step, just at random, I pick 10%. Congratulations, you got a new job, you have to move. Here in your new city, here are 2 neighborhoods. You're going to pick whichever one has more people who are like you, and what you see is that you quickly get from 50% segregation up to about 65. just looking at 2 neighborhoods. If you look at 4 neighborhoods, the level of segregation gets up to 85% pretty quickly after about 30 time steps. So this is another example where each individual agent doesn't have to do very much work. They're, first of all, applying simple rules, and they're also not trying very hard. It's not like I'm searching the entire city to find the maximum amount of segregation because I want segregation so much. I look at 2 neighborhoods, and I pick the one that seems a little bit more like me, which seems like innocuous behavior for each individual, but when you aggregate it, you get a systemic effect that is a much stronger effect than what any individual is doing. Okay, so this is an example of agent-based modeling. One of the nice things about agent-based models is that they are versatile. You can start out with something very simple, and then immediately people start asking questions like, oh, well, what if it's not 50-50? What if there's a majority? What if there are 3 kinds of people? What if Bill Bishop asks about a different kind of agent behavior? It's very easy to add more and more features to models like this. OK, so that's the first section of the tutorial on agent-based models. Let's jump into part 2, which is about cellular automata, which I still have a hard time saying. And an example that we're going to look at is called the game of life. And I'm curious to know how many people are familiar with Conway's game of life. All right. If you are, this will be maybe a nice example of the implementation. And hopefully you'll see some things you haven't seen before. If you have not seen Game of Life before, I think this will be fun. So this was proposed by John Conway, who's a mathematician, again in 1970. So as complexity science goes, this is old stuff. Made famous by Martin Gardner, who wrote a column for Scientific American for a very long time. It is similar to Schelling's model in one way, which is that it's a 2-dimensional grid where everybody is connected to their immediate neighbors. So each cell has 8 neighbors. But they don't move around. So it's not like Schelling's model where the agents are happy and unhappy and they move. Nobody moves. But what happens is that a cell is either occupied or it's not. It's either alive or dead in the language of the model. And it follows this set of rules, which is if there's a live cell that has either 2 or 3 neighbors, then it stays alive. And otherwise it dies. And if there's a dead cell that has exactly, I think it's 3, if there's a dead cell that has exactly 3 neighbors, then it comes to life. And that's it. There's kind of a long verbal way of saying that, but we're going to see it in the code in just a second. So if you load up the chapter 6 notebook, run through the first section, which is about game of life entities, and then stop when you get to the R pentomino section. And if you like, when you get to that first cell, again, when you see that HTML5, if you change that to a JS HTML, that seems to be the magic we need. So when you get to the R pentomino section, you'll see that it creates an initial state that has 5 cells in it, hence pentomino. And they're arranged in a shape that looks a little bit like the letter R, which is why it's called the R pentomino. This particular configuration is interesting because if you start with only 5 live cells, it does surprisingly elaborate things. It runs for about 1,200 steps, and during that time, many, many cells come into life and go out of life. And you notice that there are these spaceships that go flying off toward the 4 corners. Those are called gliders, if you're familiar with game of life terminology. And this is typical of a lot of game of life initial configurations, which is you can start out from almost any initial state or a random initial state. And there are a bunch of these entities, these life entities, that almost always spontaneously appear. Some of them are called still lifes because once this structure appears, it's stable. It doesn't change from one time step to the next. So if you look at the block, for example, the block is just 4 live cells surrounded by dead cells. And every one of those live cells has 3 neighbors, so it stays alive. And none of the surrounding cells has 3 neighbors, so none of them come to life. So this is a steady state. And similarly, there are these other configurations that all have this property that once you're in that state and you've got a periphery of empty cells, nothing will change. It'll be like this until the end of time. And people have given all of these entities cute names based on what they look like and how they behave. So there are things like the beehive and the boat and the tub and so on. The other pattern that shows up are various oscillators. And oscillators are also stable in the sense that they don't change. Well, they have a steady state, but it's an oscillating steady state. So if you look at that blinker, for example, it looks like it's rotating. It's not really rotating, and this is important to remember, which is that these cells are not actually moving. They're like the lights on a marquee, which is that each light is just turning on and off. But when they turn on and off in particular patterns, they create the illusion of motion. So our eye can't help but see these things as if they're moving. So those are some of the oscillators. Many of them have period 2, meaning that they just flip back and forth between 2 states. But there are examples that have long periods of repetition, like 3, 15, and I think there's a 57, an oscillator that has a period of 57. And then the other type of entity that I mentioned are periodic, but after some number of cycles, they come back to their initial configuration, shifted over, often diagonally, but there are some that also go horizontally or vertically. The most common one is a glider, which is a configuration that has either 4 or 5 on cells in its various configurations and a period of 4. So as I mentioned, when you start from almost any initial condition, you see these entities appear spontaneously. And they seem to move. They don't really move. And one of the questions I want to get at with this is, do they even exist? Are spaceships a thing? Are these entities a thing? Which might seem like a silly question to ask about game of life, but it's relevant to how we perceive the world. This is actually an old philosophical question. If you've ever heard of John Locke's socks or George Washington's axe or the ship of Theseus, these are examples from philosophy where people have really asked this question about what does it mean to be George Washington's axe if the head has been replaced 2 times over the course of history and the handle has been replaced 3 times. There are no parts of that axe that were original equipment, but yet there was at every point in time something that we could identify as George Washington's axe. Same thing, the ship of Theseus, every plank, every connector has been replaced. So this goes all the way back to Heraclitus of Ephesus, who asked Patamois tois atois, or something like that. He asked, we both step and do not step in the same rivers, we are and are not. Which you might have heard the version of that. You never step in the same river twice. And he was making a sort of obvious observation about rivers, which is that a river is not a collection of water. There's no water molecule that is part of that river now that will also be part of that river next year. The river is some kind of persistent entity that's not made up of the same stuff over time. And of course, Heraclitus was not talking entirely about rivers. He was also talking about people, because we have this property as well. There's probably no cell in your body that you were born with. So you have also replaced your head 3 times and your handle 2 times. So I think this is interesting stuff. In the book, I get into it a little bit farther if you're interested. But there's a little bit of a warning here, which is that complexity science is a philosophy black hole. Once you start thinking about these things, it's very much like the Wikipedia theory of philosophy. Do you know about this? So this is the theory that if you start from any Wikipedia page and always follow the first real link, so like not in italics and not a meta link that's about Wikipedia, follow the first link and just keep doing that, you will eventually get to the Wikipedia page on philosophy. So I would like you to try that right now. Fire up a browser, go to Wikipedia, and pick any page you like. I'll do... yes, I'm going to start from banana. All right. So anything that's in italics, that's like meta information. Don't do that. But a banana is an edible fruit. Fruit is the first, what I'm going to call a real link in this article. So I'm going to click on fruit. And then I say, OK, it's fruit. In botany, I'm going to click on botany. OK. Botany, also called plant science, is the science of plants. All right. Multicellular. Organisms, biology, natural science. Uh-oh, now we're getting close. Natural science is a branch of science. Systematic study of knowledge. Fact. Sometimes it takes a while. Sometimes you get there quickly. Reality. Physics. Oop, hang on, click the wrong one. Oh no, I'm in a loop. I got back to natural science. Anybody get to philosophy? Oh, we got one winner. About how many steps did it take? 8 steps, OK. Anybody else in a loop? Oh, OK. Oh, OK. Very good. So this often works. Sometimes you get into a loop. Obviously, it's meant to be mostly funny. There is one reason why it often happens, which is very often the first sentence of a definition says that an A is an instance of a B, where B is a more abstract category. And so when you go up levels of abstraction, you get to philosophy. OK. Ah, interesting. So the question is whether this happens in other languages, because part of what I said might just be because of the way the sentence is organized and so on. Don't know. Good question. All right.
About the game of life, Conway's game of life rules. Will you, if you start from the same state, do you always end up at the same, not the first state, but is there randomness involved? Because as I look at the rules, it looks like it's a progression.
Right, good question. Is there any randomness in game of life? And the answer is no, it's totally deterministic. In fact, in order to implement it correctly, you have to make sure that all of the agents make their decisions at the same time. So everybody looks around and sees the same state, decides what they're going to do, and then takes a step forward. Yeah, question?
We found a loop. If you start at fact, you eventually move back to fact without being philosophy.
Ah, OK, yep. Loops, I ran into a loop as well. And that is, it's possible that that's becoming more common. People have done this experiment to find out, what does the catchment basin look like? And it seems like there used to be more initial links that got to philosophy. Now it seems like there might be more loops. So I wonder if the structure of Wikipedia has evolved over time. I don't know. We might have to repeat the experiment. let me say one more thing about game of life, and then we should take a break and go get some snacks. So in just a minute. So we started with an initial state, and most of the time what happens is there's a certain amount of stuff that goes on. From some initial states, it kind of fizzles out quickly. From some initial states, it runs for a long time and produces a lot of cells. But normally, you get to something that looks like a steady state. You've got a bunch of gliders that are flying off into space. You've got a bunch of still lifes and entities and oscillators that are just sitting there. But the total number of cells usually goes up to some level and then levels off. And if there are oscillators, then it sometimes wiggles, but it's bounded by a constant. So Conway put out a conjecture that, and he was actually not saying that he thought this was true, but he wanted to challenge people to either prove it or disprove it. He wanted to conjecture that from any initial state, you will get to a steady state where the number of cells is bounded. And he offered a $50 bounty for anybody who could either prove it or disprove it. Now, if you already know the outcome, don't spoil anyone's fun. I'd like you to think about, first of all, do you think it's true or false? And how would you either prove or disprove it? And when we come back from the break, we will take a look. So I've got 10:20. Let's come back at 10:30.
not segregated. It's like segregated in the small scale, but not segregated in the larger scale, compared to if it completely split blue on one side, red on the other, where they're going to symbol work on the same.
Yes, yeah, so we'll come back from break. I was just hearing an interesting observation. Getting back to the segregation model, the definition of segregation was looking at each agent and that agent's 8 neighbors. So we were getting a very fine-grained definition. But you noticed when you saw the output from the animations that there was a certain amount of mashing up of the neighborhoods on a more coarse level. So it might be worth looking at segregation on different scales. You might see some interesting results there. Yeah, I think that's a great question. Getting back to game of life, as you're coming back from break, you might want to try out the rabbit's initial configuration. So in the notebook, we looked at the R pentomino, which is interesting because it's just 5 cells, and then it runs for a very long time. Rabbits is an example of a Methuselah, which is a very long-lived pattern. Methuselah is a character in the Bible that lived for a very long time. And rabbits, if you want to go to a command line and make sure that you're in the think complexity 2/code directory, you should be able to run that on a command line. That one's running my server. So I'm going to cd into think complexity 2 into the code subdirectory, and then I'm going to run Python life rabbits. And I'll blow that up so we can see it more clearly. So this started, if I remember right, I think it starts with 9 cells, and it runs for thousands of time steps, and it expands to fill most of the space that I've allocated for it, and it ends up producing hundreds of gliders and blocks and other entities, which is kind of fun to just sit and watch. Sometimes. We won't spend too much time on it, but it's a pretty entertaining pattern. And this again was part of the observation or the conjecture that Conway made, which is, are there any configurations that don't ever reach steady state? Configurations that just keep growing forever. And you can think about, well, what would that mean? What kind of pattern could do that? And there are 2 possibilities. There's one, which is that you could have a pattern that oscillates, and during the oscillation, if it produces a spaceship, like if it shoots off a glider, and it just keeps shooting off gliders forever, then that's an initial configuration that would produce more and more cells over time with no upper bound. The other possibility is that you could have a spaceship that moves along through space and leaves behind entities in its wake. And similarly, that would, instead of shooting off stuff, it would leave stuff behind. Either one of those patterns would refute Conway's conjecture. And the first pattern that was discovered was this, which is called Gosper's gun. And it is an oscillating pattern that generates gliders. And you can kind of see what it's made up of, which is that there are 2 blocks, one on either side, and 2 spaceships. And the spaceships are oscillating. When they hit the blocks, they turn around and come back toward the middle. When they hit each other, they produce a glider and turn around and head back toward the blocks. It is not easy to engineer patterns like this, because you can have one pattern like a spaceship that behaves very well on its own. But usually, if 2 spaceships collide with each other, they just blow up and make random stuff, and they don't do anything useful. And similarly, you can have a block. Well, a block is a steady state if you leave it alone. But by and large, if a glider or some other spaceship hits a block, normally it just blows up and does random stuff and doesn't do anything useful. So this is, from an engineering point of view, the worst possible kind of engineering. Because if there's one thing, when you build any kind of system that has multiple components, almost invariably as engineers, we want isolation. We want the different components to be isolated from each other so that I can solve problem number 1, solve problem number 2, and then put the pieces together, and they will both continue to work. And you see that in electronic systems, where by and large, when you plug one thing into another, each of the components continues to do what it was doing before, and they communicate with each other in well-defined ways. Game of Life does not do that at all. By and large, if you design two pieces that work well separately and then put them together, they just blow up and do random stuff. So we'll come back in a minute and talk about how you can possibly do engineering in an environment like that. But before that, I want to drop down a level and talk about Game of Life and show you how I implemented it in NumPy. So if you go back into the notebook, there's a section there that's called Implementing Game of Life. There's a section on Conway's conjecture, and you can run that and take a look at the glider gun. And then read through Implementing Game of Life, and we'll talk about it in a couple of minutes. OK, let me walk you through some of the code here, and I'll show you some more NumPy tricks. First part, very similar to the Schelling model. I'm going to create an array. Each cell is either alive or dead. I'm going to use 0 for dead, 1 for alive. The 1 alive is going to allow me to count up neighbors in a straightforward way. So here's a pure Python version of adding up the neighbors and applying the Game of Life rules. So I'm going to loop through all the rows I and all the columns j. And for each cell ij, I'm going to use a Python slice to get the neighborhood, the 9 cells that make up the whole neighborhood. And then I'm using np.sum to add up the neighbors. Then I have to subtract off the middle one, because I don't want to include myself. I just want the 8 neighbors. And now if I'm alive, that means, so if state is 1, that means I'm alive. Then I need either 2 or 3 neighbors. And the else means I'm dead, and I need exactly 3 neighbors. So this is a straightforward translation from game of life rules into Python. It's kind of verbose, and it's going to be super slow. Anytime you're writing for loops to do this kind of numerical computation, it's going to be slow. So the first optimization I'm going to do is to recognize that what I'm doing when I add up neighbors is very similar to what we did with the Schelling model. I'm going to break out my old friend correlate 2D. And my kernel in this case is the same as what we saw before. I've got 1s for all the neighbors and 0 in the middle. That 0 in the middle means don't count myself. All the others are going to get multiplied and then added up. So this correlate 2D, using this kernel, is going to compute the total number of alive cells that surround each cell in the array. And then I just need to check either C is equal to 3, and I don't care what the current state is, or if C is equal to 2, then I have to check to see whether I'm alive or not. And so there's the game of life rules expressed in terms of logical operations. And that's going to be reasonably efficient because computing the correlate 2D is fast. That's being done inside of nice C code, so it's going to be efficient. And then the logical operations, I'm creating a bunch of arrays. So each of the equals operations is going to create a new array, and each of the logical operations is going to create a new array. So I end up creating 4 arrays, but it's not too bad. And that'll be reasonably fast. Any questions on this? Because I'm going to make a couple of changes to make it go a little faster. Should be the same result from both methods. Is that not the case? Ah, yes, the edge behavior is different. I'm going to ignore that for now. Thank you. Good. OK. What did Conway say about wrapping the edges? I think the original intent was to treat it as if the universe is infinite. So if you run anything and it hits the edge, you just need to start adding more cells to your array. You can run this, you can wrap around, and what you create then is a world that looks like it's on a toroid or a donut shape. And that works fine. It just means that if a glider flies off one edge, it comes back in from the other. But the standard configurations, in some sense, the definition of that final state is as if it ran on an infinite grid. The explanation for why the two don't yield the same result is that I handled the boundary condition differently in the 2 cases. All right. So I'm going to make a small change to the kernel. I said a minute ago that the middle is 0 because I don't want to count myself. Instead, I'm going to make the middle equal to 10. And what this means is that if I'm alive, that counts the same as 10 neighbors. And then I'll add up the rest. And this is a clever way of encoding both my own state and the number of neighbors as a single number. Because if it's anything between 0 and 8, that means I'm not alive and I have 0 to 8 neighbors. If it's anything between 10 and 18, I think I just said alive when I meant dead. Did I? In the first case, it's dead and 0 to 8 neighbors. And then anything from 10 to 18 is alive and 0 to 8 neighbors. So now my game of life rules say that if it's 3, then I come to life. Because 3 means I'm dead and I have 3 neighbors. 12 means I'm alive and I have 2 neighbors. That means I should stay alive. And 13 means alive and 3 neighbors, and I should stay alive. Yes?
I guess I saw 1 and 0 as like categorical variables, and now you sort of turn them into continuous variables, and that's
Yes. Good question. So the observation is that in the kernels, all the kernels that we've seen so far have been zeros and ones, which seem categorical or just logical values. And now I'm being sneaky and I'm putting actual numbers in there. And yep, those can be integers or floating point values. And so you can play a lot of games with kernels. In fact, one of the things that you can do is apply finite difference methods to approximate derivatives of various kinds. That's one of the standard uses of these kernels, is things like edge detection. But for us, we're just using it for adding stuff up. But now instead of doing a plain old sum, we're doing a weighted sum. OK. This is not necessarily better, except that having made this change, I can now make one more change, which is that I can use a table lookup instead of logical arrays. And it's going to be a little bit faster because I'm going to create fewer intermediate arrays. So I'm going to apply this kernel with the 10 in the middle. So I'm doing the weighted sum. And now a table that has true 1 at locations 3, 12, and 13, and everything else is 0. And then the magic line of code is the one that says B equals table bracket C. So I'm going to take each result from the correlation, that's the C, look it up in the table, and that will give me the true or false value for the next step. The nice thing about this is that I only have to create the kernel once. I only have to create the table once. So the actual loop part is just the correlation and the table lookup. So it's a very small amount of code, and it's very efficient because it only creates one intermediate array. And now, if you go back to the terminal, you can, if you like, run life.py. Same way we ran life rabbits a minute ago. You can run life.py. And this is running a pattern that's called a puffer train. Remember, I said that there are two ways to dispute Conway's conjecture. One is the glider gun, which is a stable pattern that shoots out spaceships. This is the other way that I mentioned, which is it's actually two spaceships going along in parallel. Those two little dots on the far right are spaceships. And they interact with each other in an interesting way that makes them both stable. But they leave behind a trail of detritus that runs for a really long time and creates a lot of cells. So on an infinite grid, this will keep going forever and create an infinite or an unbounded number of cells. I'm showing you this example for two reasons. One is, as I said, it refutes Conway's conjecture. But the other is, this is a pretty big array. I think this is 1,400 by 1,000. So it's more than 1 million cells. And it's running at several frames per second in Python. And it's doing quite a lot of math. Now, it's not the most efficient algorithm. There are really efficient ways to compute life by doing hashing, like recognizing patterns and saying, OK, I've seen this pattern before. I know what it's going to do. So I'm not doing that kind of optimization, but I'm doing a reasonably efficient implementation of a simple array operation. And it's pretty fast. In fact, if you translated this into C, it would probably only get 10% faster because you would eliminate a little bit of the NumPy overhead. But the NumPy overhead for this kind of computation is not much compared to the time that you're spending doing the actual array computations. And the array computations are in C anyway. So I'm using this example. I'll shut this one down, but if you want to let yours run, you'll see that it does quite a lot of stuff. I'm using this example partly if you ever find yourself having the Python is too slow talk, where advocates of certain other languages that I won't mention are explaining that, oh, no, we can't use Python for my application because Python is an interpreted language, and interpreted languages are too slow. You know, sometimes that's true for particular computations, but for this kind of thing, by and large, if you're doing array computations using NumPy, all of the work is being done deep down inside NumPy. Often in C, or for some of those libraries, it's actually Fortran deep down inside. But it's basically going as fast as it's going to go. And Python is not adding much overhead to that. OK, let me give you one exercise to do, which is Conway's set of rules, the thing where you have to have 2 cells to come to life and 2 or 3 to stay alive. That's one of many possible sets of rules that you could have. And you can think of this table as being a way of encoding all the rules. So I created a table with 20 elements, and I put a 1 at locations 2, 12, and 13. But it would be very easy now to change this implementation to implement any other set of rules. Now, some of the rules are better than others. What you'll find is that if you have many, many ways to come to life, that what tends to happen is that the screen just fills up with live cells, and it's not very interesting. If you don't have enough rules for making new cells, then everything just dies, and it's not very interesting. And again, we get this spectrum where all the interesting stuff is in the middle. So Conway chose his particular set of rules because it's in that sweet spot where unexpected things happen. But he did identify one other set of rules that also works pretty well, same as life, except with one more rule that says that if you are a dead cell and you have exactly 6 neighbors, 6 live neighbors, then you come to life. So the exercise is to jump back into chapter 6, and you'll find a space there where I've given you some starter code. And your job is to implement high life. Here it is. And I've given you a copy of the code to modify there. So modify that so that instead of life, it does high life, and see what it does. So for this initial pattern, if you just run plain old life, this is what you get. So your job is to change the rules and then run it again, and you will see different behavior. And you could also try out what I mentioned a minute ago, which is if you add lots of ways to create new cells, see what happens, or take away some of the rules and see what happens. So this initial configuration is called replicator. If you run it with high life rules, this is what you see. So the initial pattern doubles itself, and then each of those doubles themselves. They interfere with each other in weird ways. So then you get 4 of them. And then back to just 2 of them, but now they're farther apart. And that'll repeat forever. So this is maybe a third way to disprove Conway's conjecture. This isn't a spaceship leaving behind a trail. This isn't a stable pattern shooting out spaceships. This is a pattern that replicates itself, translated in space, and then replicates and so on. And again, you can see what happens if you start adding. Let me add one more. It looks like multiples of 3 are interesting. What happens if I add 15? So this says that a live cell will survive if it has 2, 3, or 5 neighbors. No idea what will happen. Yeah, shoot.
When you talk about whether certain rule sets are interesting versus uninteresting, does that map one-to-one with whether or not those rule sets satisfy Conway's conjecture?
So when I say that a set of rules is interesting or uninteresting, does that correspond to whether or not it satisfies Conway's conjecture? I'm not sure. I think you could have something interesting in the sense that there are initial conditions that do unexpected things, and there are simple initial configurations that do big, complicated things, and yet they are all bounded. So I think you could violate Conway's conjecture and still be interesting, at least to me, but I'm not sure I've carefully defined interesting. I guess I can define uninteresting, which is if every initial pattern quickly goes to 0 cells, that's boring. And if every initial configuration obviously goes to an infinite number of cells, that's boring. It's the middle where we're not sure.
But those uninteresting examples kind of trivially satisfy Conway's conjecture.
Yes. Right. Right. So that was an example. I now have too many rules that create live cells. And what I almost always see are these lacy, fractal-looking patterns that fill up space and that just grow indefinitely. So they cover area and they grow. So it's clear that the number of cells is going to go to be unbounded. And on the flip side, if you start taking rules away, you will probably get patterns that just quickly disappear. By the way, there's a section in Think Complexity about fractals, which I mentioned just a second ago, and ways of testing to see whether something actually is a fractal or just kind of looks like it. So if you're interested, you can check that out. So let's go back to Conway's original rules, the 3, 12, 13. And let's take away the 13. See what happens. Everything just disappears. I'll run it backwards. Can you run life backwards? If you know the current state, can you figure out what the previous state was? Don't think so. There are multiple states that could lead to the same successor state, so by and large, you can't run backwards. Okay. Okay, so I want to wrap up the game of life stuff. There are a couple of themes that have emerged from this, and one of them is simple rules that yield complex behavior. And this is one of the things that keeps coming up in complexity science. I'll talk more about that in just a second. The other is the notion of emergent entities, which is things that don't exist at one low level of description, but do exist at a higher level of observation. And the spaceships in Game of Life are one of the simplest examples of that, where we know that nothing is actually moving. Each cell is either on or off, and they can turn on and off, but they don't translate through space. And yet, we cannot help seeing them as if they move. The question is that something about the world? Do those spaceships exist? Are they real? Or is that something about our visual system, which is that we just can't help inferring that something has moved when it blinks on and off? In the case of the game of life entities, that seems like it has a simple answer. But this also applies to a lot of the things that we see in the world, like rivers and George Washington's axe and mushrooms and other things that may or may not be real in the world and might just be an artifact of how we perceive the world because of how our brain is. So let me leave that alone for just a second, although I saw a question. Let me take that if you wanted to ask it. Right. Yep. Yes. Okay. I don't think I'm going to be able to paraphrase that well, but you said it really well. I wish you had a mic. But you said, yeah, in many cases, we can't define something by defining its constituent parts. We can only define it by, I think you said phenomenological criteria or something like that. And you said that's about the best we can do in terms of defining what a thing is. And I think that's true for many of the things that we point to and say, look, okay, that's a hurricane, right? What do we mean by a hurricane? It's not a particular set of air molecules. It's not a particular chunk of water or air or clouds or anything else. It's a pattern. It's a moving pattern. It's a pattern that has certain defining characteristics. Those defining characteristics were defined by us, but we find it to be a useful definition because being able to say that's a hurricane and that's not a hurricane is useful to us. It's not clear whether the hurricane cares or whether anything else cares, whether it's a hurricane or not, or if that's just a human definition. Okay, third theme that we've seen again is this idea that for many systems there are parameters that we can set, and at one extreme it's boring, at the other extreme it's boring, and it's much, much more interesting in the middle. Since this is a Python conference, I felt like I had to make at least one Python reference, or rather a Monty Python reference. Does anybody know what number 3 is a reference to? Ah, you cultural illiterates. Sometime after the tutorial, look up Anne Elk, who was part of a sketch, the Brontosaurus sketch, on Monty Python. She was a scientist who was brought on to tell what her theory was, and she went on for a long time saying, my theory about the Brontosaurus, which is my theory, is that the Brontosaurus is thin at one end, much, much thicker in the middle, and thin again at the other end. So complexity science is like that. It is boring at one end, much, much more interesting in the middle, and boring again at the other end. Stephen Wolfram has a book called A New Kind of Science, where he talks about a lot of these issues, and particularly cellular automata, and points out the first theme that I mentioned, which is that very often you have simple rules that yield complex physical behavior. And kind of like the Schelling model, that provides a counterexample to the assumption that complex behavior is caused by complex rules. That sometimes when we see complex things in the world, instead of assuming, well, I guess the world is just a complicated place, we could start looking for, maybe there are simple rules that are causing this system to behave the way it does. And in some ways, that is a triumph of science when we're able to figure out what those rules are. The other theme that I mentioned is emergence. I won't talk too much about this now, but if you get a chance to check out Emergent Universe, they have many examples there from various branches of complexity science where you'll see lots of examples. that is all I will say for now about CAs, because I can't pronounce cellular automata. And we will move on to part 3, which is about random graphs. So here's my motivating question, because you're supposed to start every example with a motivating question. Are you popular? And the answer to this question turns out to be no. And there's a cool experiment that describes this. This is an article from Scientific American. This is why you are probably less popular than your friends. And this is true of real social networks, like your actual friends in the world. It's also true of social networks, like internet social networks. So think about how many friends you have on internet, on Facebook. Okay. Now suppose that I pick one of your friends at random, and I compare you to them. And I ask, who has more friends, you or that random friend of yours that I just chose? It turns out that your random friend is more popular than you about 80% of the time, which seems weirdly paradoxical. But if you think about it, you might start to get some intuition for it, which is that when I chose you totally randomly. I was equally likely to get anybody from Facebook, or at least let's assume that that's true. And so I got an unbiased view of how many friends you have on average. But if I pick somebody and then pick one of their friends, I am getting a biased view, because the person I chose was more likely to be chosen if they had more friends, less likely to be chosen if they had fewer friends. And so it is, when I do that kind of sampling, I'm more likely to land on someone who has a lot of friends. So this is partly just a statistical illusion, but it's also a cognitive illusion, which is that you implicitly or sometimes explicitly actually perceive this, that it seems like everyone else is having more fun. It seems like everyone else is more popular than you. And there's actually a statistical reason why you get that illusion. So we're going to explore this effect a little bit. And in particular, we're going to use NetworkX, which is a nice Python library for working with data that has graph structure. I'm going to explain what that is in just a minute. Out of curiosity, how many people have used NetworkX before? OK, so some have, some haven't. That's good. You will learn something. All right. First part, here's what a graph is. A graph is a set of nodes, which are the red dots, and edges, which are the lines. And graphs in general can represent anything. So this could be like a network that says, OK, I've got a router in the middle, and it's connected to 3 other computers by Ethernet cables. But in this case, I'm using a graph to represent a social network. And what that means is that each red dot represents a person, and the line represents a friendship. So if you are friends with someone else, then your node and their node are connected by a line. And if you're not friends, then there's no line. The thing we're going to be interested in is called the degree of a node. And the degree of a node is the number of edges that it is connected to, which in a social network means number of friends. So we're going to look at different graphs that represent different social networks. And we'll look at statistical descriptions of degree and the distribution of degree. How many friends do you have, and how much variability is there from person to person? So what I mean by a statistical description is just this. This is a probability mass function that tells me for each degree how many people have that degree. So let me go back to this example graph. There are 4 people here. The one in the middle has 3 friends. And the other 3 have just 1 friend. So if I count up all the degrees, I have 3 1s and 1 3. And that's what this distribution shows. 3/4 of the population have 1 friend. And then there is 1 person, 1/4 of the population, who has 3 friends. So that's quick introduction. Let's open up. There's a notebook that's called social.ipynb. It's going to walk you through this. So run the first section, which is called graphs, and do the first exercise. And then we'll come back in a couple of minutes. If you have not used NetworkX before, you can probably figure out from the examples how this works. This creates a graph, and it adds edges to it. You can, if you want, you can create the nodes first and then create the edges. But it does the natural thing, which is if you create an edge from 4 to 2 and it hasn't seen node 4 before, it'll say, oh, OK, I'll create node 4 for you. So I'm going to add person number 4, and I'm going to make them popular. So 4 is going to be connected to 1, 2, and 3. So my social network looks like this now. So I've got 5 people numbered 0, 1, 2, 3, and 4. What I want you to get from this example is to understand the relationship between this graph structure and the distribution of degree. So for your graph, whatever you did, you might want to do this on paper and pencil. Just write down for each node how many edges does it have. So I've got a 2, 3, 2, 3, 2. So in this one, I've got 2 3s and 3 2s. So now when I make the PMF, the probability mass function, I've got 3 2s and 2 3s. That looks like this. 60% of my people have 2 friends. 40% of my people have 3 friends. Does that make sense? Any questions about how to get from a graph, compute the degree of each node, and then plot the distribution of those degrees? Questions? OK. If that's making sense, I want to go on to the next thing, which is let's go get some real data. So that graph was just 5 people, and I was just making stuff up. Turns out that the nice people at Stanford have a data set that they've made available free, which is Facebook data from a long time ago. This is Facebook data of about 4,000 people. I think Facebook has more than 4,000 now. Maybe it's like, I don't know, 10,000. Anyway, go grab this data set. If you go back into the notebook, the next section is called Facebook data. Run through that. We'll take a quick look at the data, and then we'll come back, and I want to talk about power law distributions. There's one detail here that I won't talk too much about, but just point out this estimated PDF is using kernel density estimation. If you are not familiar with KDE, kernel density estimation, it's a nice way to take a discrete sample, a sample of observations, and estimate what a smooth probability distribution function might look like. So this is one nice way of looking at what a distribution is. I also use cumulative distribution functions all the time. I didn't do that here because people are often less familiar with CDFs than with PDFs. But the CDF is actually a better way to look at data. So sometime in your life, learn about CDFs if you haven't already. So here's the key thing that I want you to see in this data set, which is, again, if I choose a random person and plot the degree distribution, I see something that looks like this. And what this says is that most people have a modest number of friends. The mode of this distribution looks like it's between 10 and 20. And 90% of the people here have maybe 100 or fewer friends. But there's a pretty long tail on this. There are a few people who, even back when there were only 4,000 people on Facebook, were friends with 700 or 800 of them. But if I do that other way of sampling, if I pick you and then I pick one of your friends at random, this is the distribution I see. So this is what I'm going to call the friend of friend distribution. And if you kind of click back and forth between these two, you see what changes. So this is the unbiased view of the actual number of friends people have. If I do the biased sampling, what happens, the whole distribution shifts to the right because I am more likely to land on people who have a lot of friends. And that thin tail, the very small number of people who have a very large number of friends, gets to be a much thicker tail because a person who has 800 friends has 800 tickets in this lottery and a much higher probability of being chosen than a person who has just one friend. And maybe one way to think about how biased this is, a person who has 0 friends has no chance at all of being selected in this process. So I mentioned this contrast between representative sampling, which means that everybody has an equal chance of being in the sample, and this biased sampling, where in particular it's being biased by the number of friends. So this is equivalent to if I handed out lottery tickets in proportional to the number of friends and then started pulling lotteries, you would be more likely to win in proportion to how many friends you have. And that's why you get this phenomenon, which is that your friends are more likely to be popular than you are. In this particular data set, I computed the mean for the two, which is on average, if I do unbiased sampling, people have about 43 friends on average. But if I sample friends of friends, it goes up to 100. It more than doubles. And this expression is the probability that your friend has more friends than you, which in this data set is about 65%. And then later on, that Scientific American article, I think they computed it, it was about 85% by the time they were looking at a bigger data set. This particular phenomenon, this way of doing biased sampling, actually comes up a lot in kind of weirdly unintuitive ways. It's called the inspection paradox, and that link there is a blog post that I wrote a few years ago talking about all the examples of the inspection paradox that I've run across. One of them is the class size paradox, which is the difference between the answer you get if you ask the dean at a college, how big are your classes? They'll give you the average class size. And, oh, well, you know, we've got some small classes like little reading seminars. We've got a couple of big introductory classes. But on average, it's 25. And you go, OK, that's great. You know, US News World rankings, 25 is the mean class size. But then you walk around the student center and you pick a student at random. And you say, how big is your class? And they'll say, 50, 100, 150. Take the average of that. It'll typically be much higher, like 40 or 50. And you go back to the dean's office and you say, you're lying. Your average class size is 40, not 25. And the dean, if they're really smart, will say, no, 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 no. You averaged across seats. I averaged across classes. That's why we got different numbers. You got a biased picture of class size because if there's a class with 300 people in it, there were 300 people walking around who will, when asked, say, my class has 300 people. If there's a reading seminar with 2 people in it, you only have 2 chances to find one of them. So you get a skewed picture of what's going on. Same thing happens when I teach statistics. I play a game with my students, and I ask them, how big is your family? And the definition I give them is I want you to include yourself, your siblings, and your parents. And I tell them, have them all tell me how many people there are. And the answer usually turns out to be in the high 3s, sometimes the low 4s. And then I tell them that actually the US Census collects this data. And the average family size by this definition is 3.1. So it's really funny that among my Olin students, it's always much higher than the national average. Why do you think that is? And they always make up stories. Oh, well, we come from a relatively educated, relatively affluent group, so maybe that has a higher average family size, or on and on and on. And all it is a sampling bias, which is that a big family has a higher probability of having a student in my class than a small family does, because every one of those children is a lottery ticket. One way to see that really clearly is that a family that has no children has no chance of showing up in my sample. And so the average immediately goes up because I've taken out all the zeros, and I've weighted all the families, all the big families, in proportion to family size. OK, yeah, question?
Are there any generic thought processes as to how to protect or detect or adjust for that?
Are there any general thought processes for how to avoid that? Well, it is an example of a biased sampling process. Yeah. So anytime you are doing sampling and trying to generalize from a sample, you need to convince yourself that your sample is representative of the population.
I get that.
Yeah.
What you showed is that it's highly probable that something is impacting it to prevent that from being the case.
That's right. It's easy to make a mistake and do non-representative sampling when you think you're doing it right.
I do a bunch of stuff with health statistics, and by definition, the only people included in the statistics have a health issue.
Yes. So the example is health.
Having a health issue don't even show up.
Right. So if you're studying health, you want to study healthy people as well as people who already have a health issue. You also want to be studying people who are dead as well as people who are currently alive. Because dead people have a tendency to leave your sample. And then death is often quite relevant to health statistics. Good. Yes. OK. So that is the inspection paradox. I wanted to mention that as a little bit of a side. I want to come back to now talking about power law distributions and scale-free networks and how these two things are connected. Because the inspection paradox is especially strong when there's a lot of variance in your data set. So if all the classes were exactly the same size, if every class was exactly 25 students, then you would get the same answer whether you ask the dean or whether you ask a student. Everybody would say 25, and the mean would be 25. The more variability there is, the more difference there is between the skewed and the unskewed view of the world. And in particular, social networks have very high variance. They belong to a particular category of distributions called power law distributions. I'm going to explain what that is and then send you back to the notebook to see an example. So how many of you are familiar with a uniform distribution? A Gaussian or a normal distribution? An exponential distribution? A power law distribution? OK, good. We got a mixture there. That's fine. So again, what I mean by distribution is a function that represents the mapping from the degree, the number of friends, to the probability of that degree. And that's one way of thinking about those graphs that we were looking at. That thing is a PMF or a PDF. I'm going to use that interchangeably. It's a mapping from each degree on the x-axis to its probability on the y-axis. Now that thing probably doesn't have any simple functional form. I could fit a polynomial to it or something. I could fit some other curve to it, but there's probably no simple mathematical shape. But I could look at the tail of that distribution and start to see, OK, once I get out into the higher numbers, maybe I could put a bound on it. Maybe I could fit a function to it. And I could think about some different functions that it might have. So if f of x, if that function I was just plotting, is a constant, then it would be a flat line. And that means that every degree has the same probability. And that's a uniform distribution. So f of x being proportional to k means it's at least approximately a uniform distribution. So what if f of x is proportional to e to the minus x? That functional form, does anybody recognize that? Do you know what distribution that is? If it decays like e to the minus x, that's an exponential function. And that thing is an exponential distribution. So if the tail decays like e to the minus x, then it's like an exponential distribution. How about e to the minus x squared? Anybody recognize that? I hear Gaussian, right. That tail behavior, if the tail of the distribution, now Gaussian is symmetric. I'm only working with a one-sided distribution, but that tail behavior like e to the minus x squared is a Gaussian kind of tail behavior. And then the last one is x raised to a power, which is to say x raised to an exponent. And that is a power law. If your distribution behaves like that last one, then it is a power law distribution. I want to give you a sense of what power laws are like, because we have intuition for Gaussian distributions. Like if I tell you that the average height in the United States is, I think for men it's 168 centimeters, and the standard deviation is about 8 centimeters. You probably have a pretty good sense for what that means. That, so maybe some people are maybe 3 or even 4 standard deviations above or below the mean. But you know that there are no adults that are 3 inches tall. And there are no adults that are 20 feet tall. And there probably never will be. Because that tail drops off so steeply. That e to the minus x squared is a really steep drop-off. So what if I made a world? I'm going to call it Pareto world, because it's the Pareto distribution that has this power law tail. In Pareto world, the average human height is the same. Let's say it's 150 centimeters, just to round it off. But it's not a Gaussian distribution. It's a Pareto distribution. How tall do you think the tallest person would be in Pareto world? So it's this weird long-tailed distribution. The mean is about 150 centimeters. But let's say I generate 7 billion people at random, and I pick the tallest one. The tallest person in Pareto world is 100 kilometers tall. Okay. So these distributions are really, really different from what our intuition is used to. So part of what the notebook is about is starting to get a feel for what these things are like. So jump back into social.ipynb and run down to the next section, which is called Power Law Distributions. Read through that, and then I'll go over it in a couple minutes. Okay, let's learn a little bit about power law distributions. As an example, I'm going to use the Zipf distribution, which is a mathematical model that happens to have the power law like exactly. It's not data that approximates it. It is literally a power law. And you can generate data from a zip distribution and then plot the PMF on these various scales. And one of the things that you quickly learn is that when you take these long-tail distributions and plot them on linear axes, you don't see anything. Everything is mashed up against the lower left corner there. And what it's showing you is that, you can think of this as Pareto world. You can think of this as the distribution of heights. Almost everybody is really, really short. They're mashed up against the left-hand side there. And there are a small number of people who are super, super tall, and they're spread out along the x-axis. But we can't really see them. So the first thing to do is take the x-axis and put it on a log scale. So this is like the log of height in Pareto world. And now at least we can see a little bit of the curve. But the real power comes from putting it onto a log-log scale. And I'll explain the math in just a second, but this allows you to, first of all, see the data clearly. And second of all, if it has a power law tail, then what you will see on a log-log scale is a straight line. Why is that true? Well, I said a minute ago, the definition of a power law tail is that this f of x, the probability density function, is proportional to x to the minus alpha. If you take the log of both sides of that equation, what you get is says that the log of the PDF is proportional to some alpha times the log of x, where alpha is the exponent. And what that equation means is that if you plot log y versus log x, you should see a straight line. And the slope of that line is alpha, which is the parameter, the exponent. Okay? So that then gives you a test. If you want to know whether something has a power law tail, you can plot the PMF on a log-log scale. If you see a straight line, that's evidence that it is a power law. If you don't, then it's probably not. So as an example, I chose the Poisson distribution, which is just a plain old ordinary distribution that does not have a power tail, and it clearly looks different when you plot it on the log-log scale. That is the Poisson distribution, clearly not a straight line. This is the Zipf distribution. Maybe not clearly a line, but maybe a line. Okay? And that gets us to this paper, which is called The Emergence of Scaling in Random Networks. This is Barabasi and Albert's paper that has now become highly cited, tens of thousands of citations, as one of the first demonstrations, first of all, that many networks in the real world have this property. The distribution of degree seems to follow a power law. And they have an explanation of why they think so many networks have this property. So let's look at the first part. This is a figure from their paper that shows on the left the distribution of degree for the actor collaboration network. So this is a network that has one node for each actor who has appeared in a Hollywood movie, and a connection between two actors if they have co-starred in a movie together. If you've played the Kevin Bacon game, you're familiar with this network. And the distribution of degrees in this network appears to follow something like a power law, at least on the right-hand side. So the right-hand side of this graph is the tail of the distribution, which is the power law tail part that we care about. Maybe we're less interested in run-of-the-mill actors. So people who have been in less than 10 movies, not so interesting. But out there on the right-hand side, you've got Michael Caine and Kevin Bacon and people who don't know how to say no to a script. The middle one is the World Wide Web as of, I think, 1989, something in that ball. No, it was later than, sorry, I forget when it was. But this is the number of connections between web pages. So each node is a web page, and a link, a hyperlink from one page to another, is a link in the graph. And that one sure looks like a good straight line. The third one is the power grid. So each node is either a power generator or a distributor, a place where power kind of comes together and gets distributed out, and the connectivities between them. So these were 3 examples that seem like they might be following power laws. And then the other one that we're looking at is social networks. So that Facebook data that we were looking at a minute ago, this is what the distribution of degree looks like on a log-log scale. And we'll talk in a minute about whether we think there's a straight line there, which would be evidence of a power law, or whether there's something else going on. So this is now getting us a step closer to understanding why you are so unpopular. The first part is that the social network has a high degree of variability. It has a power law tail. And then the other part is the question that Barabasi and Albert answered, which is why? Why does the social network have that structure, and why do these other networks have that structure? So they posited 2 parts of their model, and one of them is growth. That all of these are networks that nobody designed and built all at once. They are networks that started out small and gradually grew as more and more people joined, or actors came into movies, or power stations were added to the graph. So growth is the first part, and the other is what they call preferential attachment. And what that means is that when a new node comes and joins the graph, it connects to existing nodes, but not at random. What tends to happen is that the rich get richer, the popular get more popular, and that new links are more likely to connect up to a node that already has a lot of links. And you can think about how this happens in a social network, which is that people who have more friends will have friends of friends and a bigger group of people that would potentially connect to them. Similarly, in things like the power grid, there are probably central locations that have a lot of connections because they're central, and they're likely to get more connections because they're central. So if you have these 2 things, if you have growth and preferential attachment, you get the rich get richer phenomenon, and the tails get longer and longer. So if you take a look at the last section in social.ipynb, it'll show you a simulation of the BA model, the Barabasi and Albert model, which has these 2 properties, growth and preferential attachment. Stop when you get to the section that's called cumulative distributions, and we will come back and regroup. So let me point out just a couple of things in the code here. This function called Barabasi-Albert graph is actually from NetworkX. So one of the features that NetworkX provides is functions that will generate lots of different models of graphs. The BA graph that I'm talking about is one. There's also the Watts-Strogatz small world graph. There are things like the Holmes-Kim graph, etc. The part of this that I want you to see is, first of all, the growth part. Remember, the two features that Barabasi and Albert identify, growth and preferential attachment. The growth is basically this for loop that says that if you ask me for n nodes, I'm going to start with k nodes that are all connected to each other. And then I'm going to add the rest one at a time. And each time I add someone new, I'm going to connect them up to k others. And that way, as this thing grows, everybody has at least k connections. But when I add someone new, here's the key part. I do this random subset to choose of the nodes that already exist, which ones will I attach to. And the preferential attachment part is in this data structure, which is called repeated nodes. This is a list of all the nodes where every node is repeated by the number of times it has edges. So for every edge you have, you get overrepresented in this set so that when I draw a sample, I have preferential attachment. The more friends you have, the more likely I am to choose you. So those are the two elements. You can see them there in the code. And what you get then is the right-hand side here. That is the distribution of degree in the model. So I've used the BA model to generate a fake graph that has the same number of nodes and the same number of edges as the real graph. But I grew it using this synthetic process. And so now I'm comparing the actual results on the left with the BA model on the right. And it's clear that they are different on the left-hand side. And you probably can't see the 10 to the 1 there. So 10 to the 1 is 10. So everything from 10 on less, everyone who has fewer than 10 friends, it's pretty clear that the BA model looks very different. But after that, it's similar. It's not obvious whether it's similar enough. And this is the situation we're often in when we're looking at these power laws, is we've got a nice simple model. It seems to do what we want, but it's not clear how well it's matching the data, so I'm not sure what conclusion to draw. I'll point that out for now, but I'm going to leave it alone, other than to say we see in the real data something that looks like a power law, and now we've got a model that is at least a potential explanation of why that power law is there. Yeah. What causes the striping? Great question. At that point, we're so far out into the extreme tail that we're seeing small numbers of examples. And the probabilities, the y-axis, is always divided by n. So those are basically integers being divided by n. I think the bottommost line is 1 over n. The next one is 2 over n, 3 over n. So it's just a consequence of discrete values. Good, thank you for asking. So we're kind of in the same position with the BA model that we were with the Schelling model, which is we're trying to answer a why question. Why do social networks have this power law behavior? Barabasi and Albert are saying, oh, well, if you have growth and preferential attachment, you get power laws, and that's why the social network has power laws. And different people will find that to be a satisfying explanation to varying degrees. The obvious objection is that, well, that's not how friendships work. I don't find the most popular person around and become friends with them. And Barabasi and Albert would say, well, first of all, no, obviously that's true. We're leaving out a lot of details. But what we're trying to identify are the essential features that says any system that has growth and preferential attachment will have this behavior. I'm not saying that this is how humans behave. What I'm saying is that social networks belong to a category. It's the category of things that have these two properties. And anything in that category will have a power law. That's the nature of the argument. And it's somewhat different from the argument by analogy that we started out with. Remember when I talked about celestial mechanics, I said, my model is realistic. My model is like the world, and therefore I expect my predictions to be like what happens in the world. In complexity science, we're often making a different kind of argument. It's argument by categorical membership. And it says, not so much that my model is like the world, but my model contains exactly the essential elements it needs in order to produce the behavior. And any system in the real world that has those essential elements will produce that behavior. And my claim about this is that the criterion of what makes a good model actually gets flipped when you're making this kind of argument. That adding more realism isn't actually better when you're talking about identifying essential features. So let me explain that when you're talking about celestial mechanics, making the model more and more realistic is good, because your predictions will be more accurate. So if you take a two-body problem and you say, well, actually, Jupiter affects the Earth's orbit, so let's add Jupiter to the model, that's more realistic and the model gets better. And they say, well, then maybe I need relativity, because Mercury is moving so fast that I need relativities. And that makes your model better because it's more accurate. For this kind of argument, for a complexity argument, if I'm saying that something belongs to a category, actually simpler is better. Adding more stuff to the model doesn't make it a better explanation. Boiling it down to the simplest possible model that produces power laws is the most powerful argument. And then realism is sort of, I don't know, irrelevant? I'm not really sure what that question mark should be. OK. That is the end of random graphs. Let me pause there for a second and see if you have questions about that. And then I'm going to wrap up a little bit and send you off with some homework to do. Any questions on random graphs? Yeah?
Are there things in nature that are non-human being based that show power distribution?
Great question. Are there things in nature that are not caused by human beings that show power law distributions? Yes, it turns out that there are a lot of them. Especially in biology and especially in things like ecological webs of species that interact with other species, and things like protein interaction networks, like how genes and proteins interact.
Does that imply the potential for some natural law there?
Does that suggest that there's a natural law going on there? So let me say what I think Barabasi and Albert would say, is that those are all examples of networks that grow and have preferential attachment, and that any system that has those two properties will yield power law distributions. I think I heard someone say something else about maybe another example of a network.
I just asked about what about if you generalize to all non-organisms in non-organic sciences, power laws?
Is there anything in inorganic science where we see power laws? There are a bunch. So fractals also generate power laws in various things that you can measure. But that's probably not caused by networks. It's probably not caused by growth and preferential attachment. It's caused by other processes that yield fractals. One example of that that's in the book, I didn't talk about it today, but if you want to check it out, you can, is self-organized criticality. And those are systems that, from any initial condition, will evolve toward a critical state, which is, if you think of things like phase transitions from a solid to a liquid or a liquid to a gas, the critical state is when you're at exactly that temperature, and you tend to see the intermediate behavior, a mixture of solid and liquid. Those, that state, a critical state, is usually unstable. So if you start out with water at exactly its freezing temperature, it will tend to go toward all frozen or all liquid. It's hard to keep it at exactly that temperature unless you actively control it. So we would expect critical states to be rare in nature, because if we're not actively controlling it, we would expect to move away from the critical point. Turns out that we see critical states all the time in nature, and self-organized criticality is one possible explanation for that. And one of the defining characteristics of a critical state tends to be fractal geometry, long-tail distributions, and in a time series, pink noise. What about crystal growing? Yeah, so that's an example of a critical system. And that's an example where, left to its own devices, it will evolve toward all solid. Right, and if you wanted to keep it at a critical state, you would have to work. Okay, right. So I mentioned the book. Think Complexity is published by O'Reilly, but also available under a free license. So if you go to Green Tea Press, you can still read the first edition if you want. But you might have noticed that the repository that we use today is called Think Complexity 2. That's because I'm working on the second edition. It will probably be out in August. We are going into production over the next couple of weeks. And in fact, the early release is out now that contains a few chapters from the book. I am doing a book signing on Saturday morning, I forget exactly when, at the O'Reilly booth. And I think what I'm signing will be some early release chapters from the new book. So if you get a chance, come by, and you might get a free book. And you can even have it autographed if you want. But in the meantime, feel free to check out the book. And anytime in the next 2 weeks, if you find an error or you want to make a suggestion for improvement, please send that to me. After 2 weeks from now, I don't want to hear from you. If you find a typo, I don't want to know. A couple of suggestions for reading. If you like the graph stuff that we just did, the chapters in the book, basically 2 through 5, talk about Milgram's experiment, which is the 6 degrees of separation that you might have heard about, and the Watson-Strogatz small world graph. If you liked the cellular automata stuff, I mentioned Wolfram and some of his work with CAs. You might like chapter 5. This is the Rule 110 cellular automaton, which turns out to be Turing complete. I won't explain that right now. If you like agent-based models, we saw a little bit of chapter 9, which is Schelling's model. We saw Sugarscape go by quickly in one of the notebooks. And what you're seeing up there is an animation of Boids. This is an example of an agent-based model of herd and flock behavior. These are Boids, like birds, that follow 3 rules. So when they're flying around, if they're about to collide with someone, they avoid it. If they're near somebody, they have a tendency to line up their headings so that they're flying along together. And if they're in a flock, they generally move toward the center of the flock. And it turns out that if each agent just obeys those 3 rules, that's what you get. Things that visually look remarkably similar to the kinds of patterns that we actually see in flying birds and schools of fish and sometimes herds of animals moving over land. Yeah, question?
Is the number conserved? It looks like some are being created in this box.
I think this simulation is conserving. It's possible that they're overlapping. This is a 3-dimensional view, so they might be just overlapping. And if you like the philosophy of science stuff that I mentioned, little bits of it that appear, chapter 1 is where I propose my theory of what complexity science is all about. I want to give you a quick view of that now, and then we'll go get some lunch. So my thesis is that science is changing out from under us, that there's actually a quiet revolution going on that most people are not noticing in what we think of as a good model and what kind of explanation we're looking for when we explain the world, why it is the way it is. One piece of evidence, one way to see that things are changing, when Schelling's model first came out in the 1970s, people in the social sciences, by and large, hated it. The general reaction was, that is a ridiculously simple, unrealistic model that can't possibly do anything useful. And now, agent-based modeling is a pretty big deal in social sciences and some physical sciences. And not just that, but people really don't bat an eye anymore. If you propose an agent-based model, yeah, you can talk about it's good for some things, it's less good for other things, but it's not contentious anymore the way it used to be. So some of the ways that things are changing, I won't go through all of these, but I contrasted equation-based science, like celestial mechanics. I'm going to write differential equations, and I'm going to solve differential equations. With simulation-based science, you might notice there wasn't a whole lot of math today. We didn't write any equations to describe how these systems behave. We wrote computational rules to describe how they behave. And that's one of the ways that these things are changing. I also mentioned a little bit about how we do engineering in a world like this. I mentioned in the context of game of life, every trick that we use to do engineering, like isolation and like iterative improvement and evolution of engineered systems, doesn't work in a world where every time you make one tiny change over here, the whole system behaves totally differently. So how do you do engineering in a world that behaves like that? One of the answers is that you move away from deliberate design and move toward search. I'm going to search through a large design space to find designs that behave the way I want them to behave. And this is an example. That figure there is from an article in The Economist talking about manufacturing processes. Now that we have the ability to 3D print things, we don't have to design them in a way that lets us weld them together. We can make them any shape we want. And you can throw things like genetic algorithms at a part. So the original part is on the left. And on the right is a part that was designed by a genetic algorithm to meet the original specifications, meaning that it's just as strong or stronger than the original, but a very different looking design. And one of the things that strikes me is that the thing on the left clearly looks like it was designed by a human being. And the thing on the right looks very much like the kinds of designs we see in nature. It almost kind of looks like a knee. So if you get a chance, there's a link there to that article if you want to check that out. And then the last part that I wanted to mention is I think that there's a new kind of thinking that goes along with this kind of science and engineering, which is moving away from things like Aristotelian logic that are based on Boolean values, that things are either true or false, and tends to move toward multi-valued logic in which things are true or false to varying degrees. And a Bayesian probability is one version of that. Last thing, suggestion for some things that you might want to read. Thomas Schelling has a book called Micro Motives and Macro Behavior that talks about his original model and some of the work that followed on it. Sugarscape, which we saw go by briefly, is there's a book there called Growing Artificial Societies that's kind of one of the seminal projects in that area. And the other book that I recommend is Mitchell Resnick's book on turtles, termites, and traffic jams, which is also about agent-based models. I mentioned emergence, and I recommend this book by Stephen Johnson called Emergence. I mentioned Wolfram's book, A New Kind of Science. And Barabasi and Albert, actually just Barabasi, have a book that's about some of their work on random graphs. All of those are kind of the popular nonfiction version of this stuff, which you might find nice because they're easy to read. You also might find them frustrating because they don't quite get into the technical details that make you feel like you really understand this. That was part of my motivation for Think Complexity, is to have both the high-level discussion and also, here's the code, here's how this stuff really works. So I hope you'll find that satisfying. Two things to do. One, there's a survey link down there that you should use to tell the nice people at PyCon how wonderful this workshop was. Just remember there are 2 L's in excellent. And then the last thing, that's 4 ways that you can get in touch with me if you want to follow up with any questions or comments. So let me take just a minute here. I'll take questions if there's something that you want to talk about as a group. And then we'll disband. And if you want to talk to me one-on-one, we can do that too. Any questions or final thoughts?
Send us the
The slides, that link that's in the lower right-hand corner, that will get you the slides. Yes, question all the way in the back.
Are there any sources that directly talk about how this matter intersects with AI or engineering?
Are there any sources that talk about the connection between complexity science and AI and machine learning? I don't know any, so maybe, but I don't know one. Any other questions before we disband? I always feel bad standing between you and lunch. There's a strong disincentive to ask a question at this point. All right, thank you all very much.